over 95%. Let's just jump right into this explainer. With that staggering number, by 2030, the global demand for lithium-ion batteries is projected to consume over 95% of the currently available global lithium reserve. Just let that sink in for a second. We are literally standing on the precipice of a massive resource bottleneck, and I can tell you right now, traditional mining simply won't be enough to cross it. Welcome to this explainer. As a materials scientist, when I look at the world through the lens of elements and energy, there is absolutely no element more critical right now than lithium. Today, we're exploring the thermodynamic elegance of how we must shift from just digging up finite resources to engineering a totally renewable lithium life cycle. We are going to dive into the cutting-edge science, the real cinematic science, if you will, that is turning this impending crisis into a modern renaissance. Section 1. The global context, supply, demand, and the net zero bottleneck. Okay, to really understand this lithium gap, we've got to establish the global stakes. This isn't just a market shortage, it's a direct bottleneck to achieving global net zero emissions by 2050. The clean energy transition fundamentally relies on energy storage. Without enough lithium, the electrification of our cars and the stabilization of our renewable power grids just hit a brick wall. We're already seeing battery usage expanding to 66% of the global lithium market. And some projections show production capacity needing to exceed 6,000 gigawatt hours by 2030. That is an insatiable demand. Primary ore mining, like blasting spodumene rock and traditional solar evaporation of salt lake brines, they just can't sustain this alone. They're way too slow, and geographically, they're just too unevenly distributed. Section 2. Limits of traditional recovery, brute force chemistry. Right, so to understand the future of lithium recovery, we first have to evaluate the industrial-scale methods we've relied on for decades, and frankly, why they fall so short of our sustainability goals. Historically, we've basically relied on brute force chemistry. Look at the stark contrast between our two conventional recycling approaches here. On one hand, you have pyrometallurgy, which involves melting down materials in massive furnaces at extreme temperatures. We're talking 1100 to 1500 degrees Celsius. It wastes a ton of energy, it totally incinerates the valuable graphite, and thanks to the stability of the slag, the lithium is often just lost entirely. On the other hand, you have hydrometallurgy. This relies on dissolving spent materials in strong mineral acids, like sulfuric acid. It generates immense liquid chemical waste, emits toxic gases, and requires a ridiculously complex series of chemical precipitations to separate out the cobalt, nickel, and manganese before you even get a chance to recover the lithium. Bottom line, both methods are inefficient and way too resource heavy. Section 3. Direct lithium extraction, precision from brines. So, to pivot from brute force to precision science, we are now targeting low-concentration liquid sources. Imagine trying to extract lithium from geothermal brines that contain only 10 to 20 parts per million of lithium, or even seawater, which has a microscopic 0.17 milligrams per liter. It's literally like finding a needle in a liquid haystack. To pull this off, we need direct lithium extraction, or DLE. This relies on a whole suite of advanced mechanisms like nanofiltration, ion exchange, and electrodialysis. But a real standout here is its sorption, using inorganic ion seeds like manganese oxide spindle structures. Think of these like molecular bouncers at an exclusive club. Because of their incredibly specific lattice structure, they selectively capture only the lithium ions from a chaotic soup of sodium, magnesium, and calcium, letting the rest of the brine flow right on past. Section 4. Advanced electrochemical recovery. The ion pump. Now, this is where it gets incredibly exciting. The biggest technological leap we're making right now is moving away from complex chemical precipitation entirely and toward advanced lithium extraction, or ALE. The thermodynamic elegance here is just beautiful. Electrochemical ion pumping acts like a battery in reverse. Instead of dumping vast amounts of strong acids or toxic solvents to chemically force impurities out of a solution, we use applied electromotive force. We place a highly selective electrode into the brine, apply a specific voltage, and that electrode acts like a highly tuned sponge, absorbing only the lithium ions. The best part? It requires absolutely zero chemical reagents. You can see the brilliant architecture of these systems. By combining Faradaic intercalating electrodes with ion exchange membranes, we're effectively bridging the gap between traditional battery and capacitor systems. These setups capture lithium from complex brines or highly acidic battery leachates simply by applying an electric potential. You get rapid, room temperature extraction with unbelievable energy efficiency. You literally use electricity to pull the exact element you want right out of the water. But as a materials scientist, I have to be upfront about a core challenge here: electrode degradation. If you drop standard lithium manganese oxide electrodes into these complex brines, the manganese physically dissolves over time. So, to maintain the system's longevity, researchers are engineering incredible nanoscale solutions. By coating these electrodes with an ultra-thin aluminum-zirconium hybrid film, we're talking just 3 nanometers thick, we physically lock the manganese in place. This tiny modification drastically reduces polarization, increases the active sites, and vastly improves cycle stability, pushing the extraction capacity up cycle after cycle. Section 5. Urban mining. Spent batteries as the new ore. Think about this for a second. What if our richest lithium mines aren't actually underground, but parked right there in our garages? Millions of end-of-life lithium-ion batteries are entering the global waste stream right now. We have to fundamentally reframe how we view spent EV batteries. We can't see them as environmental hazards destined for a landfill. They are the most concentrated, valuable lithium resource on the planet. The concentration of lithium in a spent battery is astronomically higher than in even the richest natural brine. So, how do we get it out? Urban mining follows a highly deliberate sequence. We start with safe discharging or pyrolysis to strip away binders, followed by mechanical shredding and sieving. This breaks the spent batteries down into a fine, highly valuable powder we call black mass. From this black mass, we use clever techniques like froth flotation to jointly recover battery-grade graphite, which is actually 15 to 20% of a battery's weight, alongside the lithium metal oxides. And fascinatingly, studies show we can recirculate the process water up to 3 times without impacting the recovery grade, making this a highly water-efficient process. And here is an absolute stroke of genius. The traditional way to recover lithium from a spent cathode involves harsh acids, right? Well, researchers have developed an acid-free ambient recovery method. By intentionally fast charging these end-of-life batteries at high rates before we dismantle them, we induce lithium plating. We purposefully force the active lithium to concentrate as a highly reactive metal right onto the graphite anode. And because metallic lithium is so highly reactive, we can then dissolve and recover it at room temperature using literally nothing but pure distilled water. No toxic emissions, no acids, just pure thermodynamic cleverness. Section 6. Engineering a circular battery economy. Bringing all of these extraction and recovery technologies together, from nano-coated electrodes pulling lithium out of geothermal brines to the acid-free urban mining of black mass, this all leads us to our ultimate vision, the closed-loop system. I really want to leave you with this final thought. We are no longer living in an era where we can afford to just dig things up, use them once, and throw them away. By mastering the thermodynamics of electrochemical recovery and closed-loop recycling, we transform lithium from a finite consumable into a permanent renewable asset. The question isn't whether we have enough lithium in the ground to power the future. The real question is, how quickly can we scale this science to ensure the lithium we already have powers us forever?